So good morning, everyone. So to get started, what I want you to do is I want you to try to come up with a definition or an explanation or something that answers the question, what is the centripetal force? So if someone asks you, what is the centripetal force? How would you try to explain it to them? What do you think it means? What do you think comprises it? What is the centripetal force? It will take a few minutes for you to try to jot down what you think the centripetal force is. You may / probably want to look at your notes from last class to see what you might have written for that. So yeah, so we'll take a few minutes to go through this. For those just joining us, what I want you to do is I want you to think about what is the centripetal force and then try to figure out a way to explain it. And around 3 or 4 minutes or so, I'm gonna, so whenever you're ready, start typing in your response. And around 3 or 4 minutes, I'm gonna tell you to hit enter, and then we'll see how people might try to explain what the centripetal force is. So what do you think a centripetal force is? What do you remember from last class? What do your notes tell you? What do you know from your own personal knowledge? What do you think the centripetal force is? So for those of you just joining us, what I want you to do is I want you to think about what the centripetal force is. How are you trying to explain it? What do you know about it? What are the little facts you know about it? You should think about every single thing you know about the centripetal force. Um, so in a few minutes or so, I'm going to tell you to hit enter. You know, a couple of people already hit enter. That's good, jumping on it. But you might want to look at your notes, see what you remember, and then in around 2 or 3 minutes, I'm going to say hit enter, and then we'll see what people have to say about what is the centripetal force. What do you remember from last class? Let's think about another minute or so. All right, 10 seconds, get your finishing touches on how you might explain this centripetal force. 4, 3, 2, 1, whatever you have, hit enter. I want to see what people have to say about what the centripetal force is. Hit enter, hit enter, hit enter, hit enter, enter, whatever you have to say about the centripetal force. We have a lot of ideas hit enter. If you're still typing, quickly finish up your answer, and then I want to hear what you have to say. Okay, so here's what some people are saying. It says centripetal force is the force that allows for a car to make a turn, a force making the object move in a circular motion. It's a combination of forces that make up an imaginary force, represent the net force of several forces as they collectively move an object in a circular path. Centripetal force isn't actually a real elemental force, but rather a combination of mass, acceleration, and gravity, the normal force that pushes an object to the center of a circle and allows the object to move in a circle. Centripetal force is the force pushing your car in the middle of a circle to turn. It's not a real force, but rather it's a combination of various forces, including gravity, friction, and normal force. The equation for it is F centripetal is equal to mv squared over r. That's actually, I think, what a lot of people have said, what I like, is that it is the force that allows an object to move in a circle. And another thing I like what people are saying is that it's not a real force. You have to actually look at the other forces that are in the problem to think about what comprises the centripetal force. So those are all some good ideas. Centripetal force is the force that pushes and accelerates the car to the middle of a circle and allows it to turn. It's actually more of a net force necessary to accelerate the car in a circle, as various forces will combine to constitute the centripetal force, which include gravity, friction, and normal force. Mv squared of r, mass, velocity r, radius. Centripetal force is the net force resulting in the circular path of motion. Exactly. It's the force that pushes an object to the center of a circle. It's an imaginary force, more of a net force, as it's a combination of multiple forces that produce a centripetal force. Exactly. It's imaginary net force moves the object to the center of return. It's like a made-up force. It's an imaginary force that pushes the object to the middle of a circle and allows it to turn. The centripetal force is an imaginary force that pushes and accelerates the car to the middle of a circle, which allows it to turn. Exactly. So I think we pretty much summed it up. It's an imaginary force. It's basically the net force that's acting on a car. It's essentially like if a car is going around a circle, it's basically a force pushing the car essentially perpendicular so that it's being pushed into the middle of the circle. And you have to think about what are the forces that are available to us in the problem and what forces can constitute the centripetal force. So, for example, right, if a car is going around in a circle, right, you need a force that points from the car to the middle of the circle. So the force of gravity cannot be a contributor to the centripetal force because the force of gravity goes straight down. So, and you need forces that go straight to the left. So you have to think about what forces can contribute to the centripetal force that allow it to go to the left. So you'll have to think about what directions the forces are in, which can be a little bit tricky. But I would say the three main forces that you'll want to use in terms of finding centripetal forces are gravity, friction, and the normal force. I don't really know if we've learned that many other forces, but those are the three that mainly can constitute your centripetal force. So as we're continuing off of last class, the amount of centripetal force you need to make a turn is mv squared over r. So if your car is traveling at a certain velocity, v squared, if you want to make this turn on a circle of with a radius r, you need mv squared over r of force. You need that much force to push the car into the circle. It does not necessarily mean that your car has that much force available. So it's like one of those things where it's like, if your car is going around in a circle, then it means you have the amount of centripetal force you need. If you're trying to figure out whether or not your car can go in a circle, then you'll need to figure out if you have enough centripetal force available to you. So it's sort of like it's a little bit of the context of the problem. Has the car already successfully gone around the turn? Or are you trying to figure out whether or not the car can go around and turn? And that sort of will help you. Well, that sort of will give you some things to think about when in terms of figuring out the amount of centripetal force available. But the base idea is you need to have this much force to make the car go around a circle. If you don't have enough centripetal force, it won't be able to go around in the circle. So mv squared over r, a pretty important equation. Notice how it's pretty similar to the equation. Notice how it's pretty simple to the equation. Slow down. Notice how it's pretty simple. What? What's going on? Sorry, I'm trying to annotate and draw something. Give me a second. Okay, so notice how here, this is pretty similar to the equation F net, or more correctly, the sum of all forces. Notice how this is pretty similar to MA, force is equal to MA, your net force is equal to mass times acceleration. So the reason why it's very similar is because the amount of acceleration you need, the amount of acceleration you feel, this centripetal acceleration, is just v squared of r. So what the reality is, it's a more specific case of F equals ma. It's a more specific case of that. That applies to circular motion. So what I want you to do now is I just want you to quickly figure out how much centripetal force this car is experiencing. So this car, it's a 100-kilogram car that is successfully going around in a circle. So it is successfully going around in a circle with a radius of 10 meters at a velocity of 20 meters per second. So I just want you to quickly figure out what is the amount of centripetal force that the car is experiencing. And then I want you to think about what force do you think is producing this centripetal force. The second one is kind of tricky. The first one is just sort of like a very, plug and chug, see what you get. The second one is more important. What force do you think is producing this centripetal force? Because you can't just say that the car is experiencing this centripetal force without identifying which forces are actually producing this centripetal force. If there are no forces involved, then you can't have this centripetal force. So why don't you just quickly take a few minutes. How much force is this car experiencing? If it is 100 kilograms of mass, is a radius of 10 meters with a velocity of 20 meters per second. So how much centripetal force is the car experiencing? And then I want you to figure out what force do you think is producing this centripetal force? And so the second question, it's also probably helpful to draw a free body diagram and to help you visualize what forces could potentially produce this centripetal force. Take a couple of minutes. I'm very curious to see what you guys have to say in terms of what force you think contributes to centripetal force. It's kind of a tricky one. honestly, a lot of the times finding the centripetal force, what contributes to it is honestly a huge part of the challenge. I think, yeah, it's a huge part of the challenge trying to figure out what contributes to your centripetal force. Take another minute or so, and then I'm going to at least just go over the problem really quickly, at least the math part, and then I will talk a little bit more about the what composes the centripetal force. So in terms of finding the centripetal force, right, the equation for it is your centripetal force is an equal mv squared over r. And so in this particular problem here, the mass of our car, so I'm just going to plug in the stuff we know into this equation. So the mass we have is 100, the velocity we have is 20, so 100 times 20 squared. And then we're going to divide it by the radius, which is 10. So when we do this all out, what we get is 100 times 20 squared, which is 400, divided by 10. And this should equal 4,000 newtons. So pretty straightforward here. So I don't think the math part of this is going to be that challenging. The part that is going to be challenging, though, is figuring out what actually produces this centripetal force, because it's not intuitive at all. So what I'm going to do is I'm going to draw a free body diagram for this car. So in this particular case, what we have is we have the car. And so as usual, it's on the road. So what that means is you have the force of gravity going down, and then you have the normal force going up, right? So the gravity is pushing the car down, and then you have the normal force going up. However, if the car is, let's say the car is turning this way, it's going around this way. What you need is a force pushing the car to the middle. And so what could that force be? Well, in this particular case, what it is it's actually the force of friction. So if the car is going around in a circle counterclockwise, the friction in the road is essentially pushing the tires inwards. And so if there wasn't any friction in the roads, this car wouldn't be able to make the turn. So your gravitational force is going straight down. And so notice how the direction you need for the centripetal force is into the circle. However, your gravitational force is going straight down. So your gravitational force can't produce, it can't possibly produce any can't possibly contribute at all to centripetal force. And that's the same for the normal force, right? The normal force is going straight up because it's resisting, the force of gravity. And so the normal force is going straight up. So this also can't contribute to our centripetal force. And so the only force that makes sense left is the force of friction, which is the friction from the roads and the tires that pushing the car inwards into the circle. And so the amount of friction force you have available determines how much centripetal force you have. So if you have a high amount of friction, so this might be something like asphalt, right? You can produce more centripetal force. So your car can make crazier turns. You can go at them at faster speeds, or you can turn on a smaller radius. However, if you have like a surface that's wet or ice or something, where you have a low amount of friction, then your car won't be able to do those crazy maneuvers. It'll either have to take the turn slower or it'll have to take wider turns because there's not as much centripetal force available to you. So really, this force of friction is in this particular case, that is the force that is contributing to your centripetal force. Now, that doesn't mean that that doesn't mean that the normal force and the force of gravity will never contribute. That's not true. They sometimes will contribute to your centripetal force. However, you have to be careful. You have to be looking at what direction these different forces are going in, and you have to do a little bit of thinking yourself. So yeah. Does anyone have any questions about that? About okay. So another way of thinking about it is that the net force on the object is the same as the centripetal force on the object, which is the same as the sum of all forces on the object, which has to equal mv squared over r. So if you're going extremely fast, you're going to need a lot of centripetal force to push you around in a circle. So if the forces involved in the problem are not enough to generate enough, or aren't enough to generate enough centripetal force. Oh yeah, sorry. Yeah, okay. Yeah, sorry. So you can also think of it as the net force is equal to the centripetal force, which is going to equal the sum of all forces, which is going to equal mv squared of r. So the thing is, if you're going extremely fast, your v squared is going to be very big, which means that you will need a lot of centripetal force in order to push you around in a circle. So if the forces involved in the problem aren't enough to generate enough centripetal force, then you're not going to be able to move around in a circle. Your car is going to essentially resist that, and it's probably just going to go in a straight line, or it's just going to swerve or something. As you saw on Tuesday, what happens when I was driving a car when I was trying to make a turn very quickly. I ran a very sharp turn. The amount of centripetal force available to me was not enough, and so my car was basically just didn't want to make that turn. So for example, if a 1 kilogram car traveling at 1 meters per second or on a turn of 1 meters, well, it's going to need 1 newtons of centripetal force towards this middle of the turn to make the turn successfully. So you need so in this particular case, this 1 kilogram car needs 1 newton of centripetal force to push the car towards the middle of the circle. However, if the friction from the road, if that can only generate half a newton, so 0.5 newtons of force into the middle of the circle, then the car won't be able to make the turn because the centripetal force you need exceeds the amount of centripetal force you're able to generate from the road. So either there has to be another force in the problem that allows you to produce enough centripetal force, or the car just won't be able to make the turn. So in this particular case, the car won't be able to make the turn because there's no other force available. In other cases, there might be another force available for the car, but you need enough centripetal force in order to make the turn. So you can think about it as mv squared of r. That's like the minimum amount of centripetal force you need in order to make the turn. Anything less than that, you won't. Anything less that the car is able to access, it won't be able to make that turn. So one of the main ways you will see centripetal force like in real life is when we talk about something called G-forces, which you may or may not have heard about, but I feel like most people have at least talked about G-forces maybe once in your life. So G-forces, what G-forces are, it's just another way of measuring acceleration. And this is especially true in circular motion. A lot of times when you're measuring the acceleration of objects that are going in circles, oftentimes you're actually measuring it in terms of G-forces, not in terms of meters per second squared. What's kind of weird about G-forces is it's actually misleading. What a G-force is measuring is you're not actually measuring the force, you're actually measuring the acceleration that you're undergoing. So this can be kind of misleading because it says G-force, so you're probably thinking like, I need to measure the force. But in reality, what you're doing is you're measuring the acceleration of an object relative to that of gravity. So you're comparing the acceleration of the force you are experiencing to the acceleration due to gravity. So let's say hypothetically that your car was going around in a circle, and the centripetal force on the car was 9.8 meters per second squared. So that would mean you would feel a g-force of 1. Because the amount of force you're available, amount of centripetal force you're, the amount of centripetal acceleration you're feeling is the same as acceleration due to gravity. So you would only be experiencing 1 g of force. Now, if you have a g-force of 2, what that means is you're going to experience an acceleration equal to double that of gravity, which means that you would be accelerating at 19.6 meters per second squared. If you're feeling a g-force of 3, that means you're experiencing an acceleration of 29.4 meters per second squared, which just basically just means 3 times the acceleration due to gravity. And last but not least, if you're accelerating at 4.9 meters per second squared, right, then you're experiencing a g-force of 0.5 g. So g-forces are honestly probably one of the most practical uses of centripetal forces. If you're doing any sort of engineering or anything like that, a lot of times you will have to consider g-forces, and we'll see why in a second. So it's good to understand what a g-force is. You've also a lot of times you might have like read or watched stuff with like space or like fighter pilots or something, and they're like telling you about, or roller coasters, and they're telling you about how many g's of force you're experiencing. Well, that's what this is about. It's basically telling you how much what your centripetal acceleration is in that particular or acceleration in that particular instance. So in terms of when g-forces are used, they're generally used to measure I said measure the force. I mean measure the acceleration a person might experience in a circle, that a person might experience if they're going around in a circle, or if they're going up or down very quickly. So this means that it's particularly relevant in stuff like aviation, car collisions, and roller coasters. So we're going to be looking at a lot about roller coasters. We're not going to be looking as much at aviation or car collisions. Car collisions are particularly interesting. If your car crashes in a serious car accident, you feel a lot of g-forces. You've experienced a huge amount of g-force. It can be very dangerous. And the thing about g-force, the reason why g-force is so important in terms of engineering and stuff, is that there is a limit to how much g-force your body can tolerate. So if you feel too much g-force on you, what that could happen is that you could black out, you could lose vision, you could lose consciousness, or you could even die if you experience too much g-force. So, and it's also kind of weird is that the amount of g-force your body can tolerate depends on which direction you're going, essentially. If you're going up, down, your body cannot experience as much g-force as it can going left, right, essentially. So if you're accelerating horizontally or decelerating horizontally very quickly, you can experience a lot of g-force. If you're going up, down very quickly, you can't experience as much g-force. I think most people, if you're going up or down, most people black out under 10 newtons of g-force. Whereas going left to right, people have experienced much more than that. I think there's one person who was in the Indy 500 and they got into a really bad car accident during the race, and they experienced a g-force of I think 213 g's, which is 213 times the force of gravity, which means you would be going 2,000 meters per second squared. Your acceleration would be like 2,000 meters per second squared, which is absurd. They actually did survive. They did survive. That's actually wild. They felt 213 G's of acceleration, and somehow they just survived. Luckily, it was very, very because car accidents are very, very short in terms of the time. How many meters per second is the speed of sound? So the speed of sound is about like 750. No, it's about like 700 miles an hour, which is probably around like 300 to 350 meters per second. About 300 to 350 meters per second, somewhere around that range. Yeah. So we're going to be looking at quite a bit of roller coasters this last sort of part of the forces, because roller coasters I think are really interesting. So we're going to be looking at roller coasters quite a bit. So what we're going to do now is we're going to do a few practice problems of centripetal force. I think this will be very helpful because centripetal force is probably one of the, it's not, I don't think it's, well, centripetal force can actually be pretty hard. It depends on the context of it, because it gets really weird very quickly. But we're going to start off with some more simple ones. So what we're going to do is we're going to look at this particular problem. A motorcycle is driven around a 12-meter tall vertical circular track at a constant speed of 11 meters per second. So that means so from the bottom of the track to the top of the track, that's 12 meters tall. So what that means is, and it's going around at a constant speed of 11 meters per second. So when the motorcycle is on the left side, so I on the left side, what forces constitute the centripetal force? And then what are the magnitudes of the forces? So you want to identify what force is contributing to the centripetal force here, and what other magnitudes of the forces involved. So I'm gonna go through this first problem here. We'll take a look at it. Let's take a gander. So I guess we can think about it as, okay, I guess let's first start with finding the magnitude of the force. Yeah, I think that's easier. So we know that the motorcycle is successfully going around the turn. So we don't really have to worry about like finding whether or not it can go around the turn, which makes our life a lot easier. So if the motorcycle is successfully going around this turn, what this means is that the centripetal force the motorcycle is experiencing has to equal mv squared over r. Right. So that's how much centripetal force the motorcycle needs to go around the circle. And so the mass of the motorcycle is 250. It's going around at a velocity of 11. In this particular case, the loop is 12 meters tall, which means that the radius of this is going to be 6. And so that means, oh, this should be 11 squared. Sorry. Velocity should be squared. And so what we get is 5,041. So the motorcycle needs about 5,041 newtons of force to figure it out. So, okay, so this is the total amount of centripetal force the roller coaster experience, the motorcycle experiences. So, and however, what could be happening is that there are a lot of forces contributing to this centripetal force, but the overall magnitude of the centripetal force is 5,041. So now we need to think about what forces are contributing to the centripetal force. So first off, as usual, the force of gravity, there's a force of gravity going straight down. So we need a centripetal force going this way, but the force of gravity is going straight down. So that means the force of gravity can't contribute to our centripetal force again. However, if you notice here, the motorcycle is resting on the track here. Well, it's not resting, but it's sitting on the track, which essentially means that as the motorcycle is on the track is going to be exerting a normal force onto the motorcycle. So there is a normal force being pushed out the motorcycle, pushing the motorcycle into the middle. Notice here how the normal force is not going straight up, right? Because the motorcycle, right? There's no track below the motorcycle. Like the track is on this side. So, and the track is going to push the roller coaster perpendicular to the track. And so in this case, the normal force is not parallel, is not the other direction of gravity. It's actually perpendicular to it. So I think that can be really weird because a lot of times your natural instinct is up as normal force, down as gravity. And this is one of those cases where, in this case, the normal force almost has nothing to do with the force of gravity here. Yeah. So the normal force is pushing us straight to the inside, the force of gravity going straight down. You could also argue that because the motorcycle is going up, there is a friction force going down here. But ultimately it doesn't really matter because the friction force, it's in the same direction as the force of gravity. It's perpendicular to the centripetal force. So it's not helping us at all. So it doesn't matter whether or not there's a friction force. The only force that's contributing to our centripetal force is our force of gravity. Is our normal force. So since we only have a normal force, what this means is that the sum of all forces should equal 5,041. And so the only force that's acting pushing the motorcycle into the turn in the middle of the turn is the normal force. It just means our normal force is producing the entirety of this force. So this is the case where the normal force is doing all of the work for us. There's no other force that's contributing to the centripetal force in this particular section. Anyone have any questions about this? It's kind of weird. The next one will be a little bit weirder. So so this problem is different. I know it looks very similar, but it is different. This time, what we're looking at is, instead of looking at the side, we're looking at the top. So when the motorcycle is at the top, what forces are contributing to the centripetal force, and what are the magnitudes of these forces? So this problem, I don't know if it might be easier, it might be harder. I'm not really sure, but the idea is the same. What forces are contributing to the centripetal force, and what are the magnitudes of the forces involved? So I'm going to go through this one. This one, I don't know. Well, I mean, I think I think it might be easier to understand. I'm not actually sure. We'll figure it out. Okay. So some things are the same. So first off, the amount of centripetal force in the problem will be the same. It's still going to be 5,041. Right? That's because the object is moving around in a circle. The velocity hasn't changed. The radius hasn't changed. The mass has changed. So all of the forces add together should still equal 5,041. However, because the motorcycle is on the top now, what this means is that the individual contributions to this centripetal force might be different. And so in this particular case, now let's look at this problem here. What are the forces acting on this motorcycle? So this time the motorcycle is being pulled down by gravity, going straight down, and it's also being pulled down by the normal force. And that's because the motorcycle is touching the top of the loop. And so if something is touching the top of the loop itself is going to exert a force back onto the object. So this is, the normal force is basically when two objects are in contact with each other, and they're both going to exert a force on each other. So the normal force is going to exert a force pushing the motorcycle into the loop, and the force of gravity is going to push the motorcycle into the loop as well. So this time we actually have two forces contributing to our centripetal force. And the sum of these contributions will equal 5,041. So what this means that the sum of all forces here is going to equal my centripetal force. In this case, the sum of all forces here include my force of gravity. So the force of gravity plus my normal force should equal 5,041. The force of gravity is mass times g, which is 250 times 9.8. 250 times 9.8 is, what is that? 2450. So what I get is that 2450 plus normal force is going to equal 541, which means my normal force should equal 2591. And 2450 is my gravitational force. So, oh, you can't see the board. Gosh. Okay. A lot of the things are the same. The overall amount of centripetal force is the same. It's still 5,041. However, this time, because the motorcycle is on the top, the things that contribute to the centripetal force are going to be different. The force of gravity on this motorcycle is going to point straight down as usual. Nothing has changed. And because the motorcycle is touching the loop is also going to touch the motorcycle. And so the loop is going to push onto the motorcycle. And that push is called the normal force. So in this case, we have two forces both pushing the motorcycle into the loop, which is the normal force and the force of gravity. So this time we have two forces contributing to the centripetal force, which means that the sum of these two forces should equal my centripetal force, which we found last time. This doesn't change at all. So that basically means my force of gravity plus my normal force should equal 5,041. And then I just solve this normally. The gravitational force is 250 times 9.8. And then my normal force should equal the difference between that. So, right, solving for the centripetal force itself is not hard. I think hardest part is identifying which forces are contributing to the centripetal force. Once you are able to do that, it's not that. It's at least this is pretty straightforward. The hardest part is recognizing what forces are contributing to the centripetal force. Okay. So centripetal force can get very nasty very quickly because, as you can tell, the hardest part is identifying which forces are pushing it into the middle, and this gets really hard once things start getting harder. But we won't get there yet. But it can get really hard very quickly. So this time, what I want you to do is, okay. So the next problem it's the same idea. It's just that at the top of the roller coaster, how many G's of force do the riders experience? I think we'll skip this one. Basically, what you do for this is you just find the acceleration, which is pretty easy. So you basically just take the centripetal force, you divide it by the mass, You get your acceleration, which is like about 20 or so. So if you divide this by acceleration due to gravity, you get a g-force of roughly 2. So that's pretty much just what it was asking for. It's just asking you to find the acceleration and then compare that to the force of gravity. We're gonna skip it just for now, just because we only have time for one more problem. And I don't think that this is the most complicated one. There is one more problem that I wanted us to look at, and this is what happens when the car is going around the circle, and we're looking at the force of friction here. Here we go. Okay, so in this particular problem here, a 500 kilogram car is entering a turn with a radius of 25 meters at a velocity of 15 meters per second. So the road itself has a coefficient of kinetic friction of 0.25. So what I want you to do is I want you to figure out, will the car be able to make the turn successfully? Just due to the sake of timing, I'm just going to start going through this. But I'm just going to go through the first few parts because we already sort of looked at this. So this problem is very similar to the one we just did earlier. So I'm just going to go through some of this really quickly. To the binding centripetal force, this is just mv squared over r, which in this case is 500 times 15 squared over 25, which is 4,500. So you need 4,500 newtons of centripetal force. So that's just plugging it in, not too complicated. The hardest part is going to be looking at what forces contribute to the centripetal force. So if we draw a free body diagram, we have the force of gravity going straight, force of normal force going straight up, force of gravity going straight down. and then we have the friction force going to the left or right, which depending which angle you're looking at. So this is the exact same as what we did earlier. What we need to do now is we need to figure out, is our friction force able to produce 4,500 newtons of force? Our normal force and our force of gravity do not contribute to our centripetal force. So we don't, when we're looking at the centripetal force, we're not including these ideas in there. So what we need is we need the friction force to be at least be able to produce 45. We need to at least be able to produce 4,500 newtons of force. So our force of friction here is going to equal my coefficient of kinetic friction, mu k, times my normal force. This is just a definition of friction. The force of normal force here, in this case, is just going to equal mg. Because force of gravity is pulling the car straight down. The normal force is supporting it to prevent it from falling. So it's just going to equal mass times gravity. So what we get is that my force of friction should equal 0.25 times the mass, which is 500, 1.8. And so we get to the force of friction is only able to produce a force of 12.5 newtons. So as a quick recap, what did I do? I just solved for how much centripetal force you need just by plugging stuff in. I then identified which force is contributing to my centripetal force, which is just the force of friction. So then what we need to do is I need to figure out if my force of friction can produce more force than my centripetal force. So then what I did is I just solved for the friction force, which is mu k times normal force. The normal force in this case is just going to equal my gravitational force because the car isn't falling to the ground, so the ground needs to support the car. So that just simplifies into mu k times m times g. I plug everything in and I get a friction force of 1225, which is smaller than the force we need. So unfortunately, the car cannot make this turn because it is moving too fast. Okay, so we're out of time. It's 9:55. So we will continue this after the break. Yeah, I have a nice spring break. We don't have any homework over spring break. That would just be absurd. So you don't have any homework over spring break, and we'll continue with centripetal force when we get back. I'm looking forward to seeing some of you in person. I think that'll be interesting. But other than that, I'll see you guys. Oh, isn't it just the exit ticket left? Oh, yes, there is the exit ticket left. If you want to just quickly do that. Yeah, you can just quickly do that. I think it's very similar to the warm-up question. But other than that, I'll see you guys after the break. Yeah, you can just hammer through the exit ticket really quickly.